Today, we're going to solve a puzzle that, at first, seems totally impossible. And our tools? Well, they're not magnifying glasses or fingerprint dust, but angles, sides, and one of the most powerful ideas in all of geometry, congruent triangles.
So let me ask you something. Imagine you're standing on the bank of a huge river, and you need to know exactly how wide it is. You can't just stretch a tape measure across it, right? So how would you do it? How do you measure something you physically cannot reach? Picture this. You're on one side of a massive canyon, and you need to know the precise distance to the other side. There's no bridge, no way to get across. It feels like an unsolvable problem, a total dead end.
And listen, this isn't just some brain teaser. It's a real-world problem that surveyors, engineers, and even ancient astronomers had to figure out. How do you measure the immeasurable? That's our central mystery today.
It turns out the answer isn't a bigger tool, it's a way smarter idea. The solution is all about logic and the amazing properties of the most stable shape in the universe, the triangle. So what is this big secret? It's actually beautifully simple. If you can't measure the thing you want to measure, you just create a perfect, identical copy of it somewhere that you can measure. And in geometry, these perfect copies have a special name. They're called congruent polygons. The easiest way to think about them is as identical twins in the world of shapes. Every single corresponding angle is the same, every corresponding side is the same length. They are perfect duplicates of each other. This idea is so important, it's got its own acronym, CPCTC. I know, it's a bit of a mouthful, but it stands for corresponding parts of congruent triangles are congruent. And trust me, this is the master key to our whole puzzle. It basically means if we can prove two triangles are identical, then we automatically know all their matching parts are equal. Okay, but wait a second. That still sounds like a ton of work. To prove two triangles are identical, do we really have to measure all three sides and all three angles? That's 6 different measurements for just one problem. Well, luckily for us, the answer is a big, resounding no. You see, mathematicians discovered a set of brilliant shortcuts, what I like to call a detective's toolkit, that lets us prove two triangles are congruent with way, way less information. These are the 4 secret codes in our detective's toolkit. If we can spot any of these patterns of clues, SSS, SAS, ASA, or AAS, we've cracked the case and proven the triangles are identical. So let's take a super quick look at each one. First up, we've got SSS, which is just side, side, side. This one's the most straightforward. If you have 2 triangles and you can show that all 3 sides of one match the 3 sides of the other, they have to be identical. You just can't build them any other way. Next is SAS, or side angle side. Now the key here, and this is super important, is the included angle. It means the angle has to be literally sandwiched between the 2 sides you know. If you've got that combo on both triangles, they're congruent. Then we have ASA, angle side angle. Kind of the reverse of the last one, right? If you know 2 angles and the side that connects them, the included side, are the same on both triangles, you've proven they are perfect copies. And finally, there's AAS, angle, angle, side. Here you have 2 angles and a side that's not between them. And this one works because, think about it, if you know 2 angles in a triangle, you automatically know what the third one is. And that just turns it back into the ASA pattern we just saw. So it's another totally reliable way to prove congruence. Okay, toolkit assembled. We have our 4 secret codes, SSS, SAS, ASA, and AAS. Now, let's go back to that river and put these tools to work. So how does a surveyor actually do this? Well, first, they pick a point B, like a tree or a rock, on the other side of the river. Then, from their own side at point A, they walk a straight line at a right angle to the river to a point C. Next, they find the exact midpoint of that line, which we'll call E. And finally, they walk in a straight line away from C, making sure that points D, E, and B are always lined up. This whole clever setup creates a second triangle that we can now use to solve the whole puzzle. All right, let's gather the evidence. Clue number 1, the surveyor created 2 right angles. And since all right angles are 90 degrees, we know for a fact that angle C in our first triangle and angle D in our second one are congruent. That's our first A for angle. Now for clue number 2. Remember point E? It was the midpoint of that line from A to C.
By definition, a midpoint splits a line into two perfectly equal halves. So the side EA of the first triangle is congruent to the side CE of our new triangle, and that's our S for side.
And for our final clue, look at point E again. The lines BD and AC cross right there. Angles on opposite sides of intersecting lines are called vertical angles, and a fundamental rule of geometry is that vertical angles are always congruent. So angle AEB is a perfect match for angle CED. That's our second A. So let's put the clues together. We have an angle, the included side, and another angle. Hey, that's the ASA pattern. We've done it. We've cracked the case. We have proven, without a shadow of a doubt, that the triangle across the river is a perfect identical copy of the one we just made on our side. And now we use our master key, CPCTC. Because the triangles are identical, their corresponding parts must be equal. This means the width of the river, AB, the part we couldn't measure, is exactly the same as the side DC, the part we just paced out on land. So if we measure that side and find it's 550 meters, we know the river is 550 meters wide. The impossible has been measured. Case closed. You know, this isn't just a clever trick for surveyors. The principles of triangle congruence and the stability they provide are, quite literally, the foundation of the world all around us.
Just look around you. Every time you see a bicycle frame, a radio tower, or a bridge, you're seeing congruence in action. The reason engineers use triangles for everything is because of what we just learned. A triangle's shape is locked in by the length of its sides. It can't be bent or deformed. This incredible rigidity, all thanks to our congruence shortcuts, is what makes these structures so incredibly strong and stable. So now you have the detective's toolkit. The next time you see a bridge or look up at a skyscraper, you'll see it differently. You'll see that hidden network of congruent triangles, the secret code of geometry that's quietly and reliably holding our entire world together.